Yeah, welcome. So the topic we'll be discussing in this lecture is B plus tree. So B plus tree in most of the context it is very similar to B trees, but there are certain key differences. So which we'll be discussing here, right? So B plus tree is a close cousin of B tree. Of course, it is very much similar to B tree. It is also one type of MBA search tree, right? B plus trees are heavily applied in database applications. Okay, in database management system, they are heavily used because they use something called as indexes. So, which is very much connected with database managing the databases. So B plus tree, one of the application of B plus tree is DBMS. First, let us try to understand what are the core differences between a B tree and a B plus tree. Okay. In a B plus tree, we have two types of node. One is called as index node, the other one is called as data node. Index node will not contain any data. It will have some key. It will have some key, but these keys are not data. These are called as indexes. These are called as indexes. Okay. So index means it is something like a pointer. It is something like a pointer, right? So these are called as indexers. Index means pointers, right? Okay. So just as of now, you understand this much. What is the index? What is the data? All these things we'll be discussing in detail, right? Okay. And data will be available only in leaf nodes. So leaf nodes are otherwise called as data nodes. Data will be available only in leaf node. So leaf nodes are otherwise called as data nodes. Okay. All other nodes will have key, but these keys are not actual data. These keys are indexes. Right? Okay. And data nodes, all the data nodes will be linked together. All the data nodes in the leaf node, all the data nodes will be linked together. Something like a linked list. Something like a linked list. They will be linked together. Okay. And the data nodes will contain only data. They will not have any pointer. Okay. So this data node contains something 1 and 5. So it contains only data. It will not have any further pointers. It is not that there is a pointer here which is pointing to null, or there is a pointer to the right of 1 which is pointing to null, or there is a pointer to the right of 5 which is not pointing to null. No, there is no pointer at all. Data node contains only data, and data is available only in the leaf node. So leaf node are called as data nodes, but all these data nodes will be interconnected through a pointer, right? So this is the key difference between the B trees and B plus tree. So there are two main differences. What are they? B plus tree will have two types of node. One is index and the other one is data node. Index node contains only indexes or pointers, whereas data node contains the actual data, and these data are available only in the leaf node. Right? Leaf node contains only data, they don't have any pointers. But all these leaf nodes will be interconnected through a link. Right? Now let us officially define what is meant by a B plus tree. Okay, a B plus tree of order M is either empty or it satisfies the following properties. Okay, the first property says that all data nodes. Okay, all data nodes are at the this is not all just all data nodes are at the same level and or leaves. All data nodes are at the same level and or leaves. Data node contains only elements, that is, it contains only data. Otherwise, instead of data, we will call it as element. Okay, they don't have any pointers. They don't have any pointers. Okay? Whereas the index node, what is the property of a index node? The property of an index node is same as that of the property of a B tree of order M. That's it, nothing else. Okay. So this is how we define the B plus tree. A B plus tree of order M is a tree which is either empty or it satisfies the following two conditions. The first condition says that all the data node should be leaf nodes, and these nodes should contain only elements or data, and they should not have any pointers. What about the index node? Here, what is meant by index node? The node other than the data nodes or index nodes. All nodes other than the data node or index nodes. Okay, that is all including root node and all intermediate node are called as index node. What is the property of an index node? The property of the index node is same as that of the property of a B tree of order m. That's all. Okay. So each index node will have keys, will have certain number of keys depending on its order. Okay. A B tree of order m, it can have maximum m minus 1 keys. Okay. And minimum it can have seal of m by 2 minus 1 keys. Okay. Accordingly, it will have that many keys. But these keys are not elements, they are just indexes. These keys are not elements, they are just indexes. Okay. In a B plus tree, actual element will be available only in the leaf node, which is called as data nodes. Right. Okay. So this is how we define a B plus tree. Right. Okay. Here one more catch is there. One more catch is there. The what? How many elements can be there in a data node? How many elements can be there in a data node? Okay. How many? Normally, how many keys can be there in a B tree? In a B tree, how many keys in a B tree of order m? Any node can have m minus 1 keys maximum, and minimum. This is the upper bound. This is the upper bound. That is maximum. It can have m minus 1 keys. Okay. And minimum it can have how many keys? Seal of m by 2 minus 1 keys. Okay. Seal of m by 2 minus 1 keys. So this is the lower bound for a B tree, right? Okay. Now for a B plus tree, this is true. This is true for the root node and for index nodes. This is true for the root node and for the index node. Okay. Root node can have maximum m minus 1 keys, and all the index node also can have maximum m minus 1 keys. Okay. Root node can, all the index node can have minimum seal of m by 2 minus 1 keys, and root node can have minimum 1 key, right? Minimum 1 key. Okay. So this property of B tree is applicable for B plus trees also, but it is applicable only for root node and for index nodes. It is not applicable for the leaf node or the data nodes. Okay. The capacity of the data node need not be same as that of the index node. Okay, this is one point, important point. The capacity of the data nodes need not be same as that of the index node. What is the capacity of an index node of order m? Capacity means maximum, upper bound, m minus 1. Okay. That doesn't mean that data node's capacity also should be equal to m minus 1. It can be greater than that also. Okay. Or it may be m minus 1 also. If it is m minus 1 also, there is no issue. But there is no compulsion that it should be m minus 1. That's what I wanted to say. Okay. The capacity of the data node need not be same as that of the index nodes. Okay. Fine. So please make a mark of this. Right. So what will be then what is the capacity of the data node? That depends. Whatever we want, we can set. Let us assume that the capacity of the data node is C. Let us assume that the capacity of data node is C. So that is the upper bound. That is the upper bound. That is, data node cannot have more than C elements. Okay. Then what is the lower bound? When the lower bound is given as seal of C by 2, then its lower bound is seal of C by 2. That is, at any point of time, any data node should not have less than seal of C by 2 keys. Okay. If at some situation, if the data node contains if it contains less than seal of C by 2 keys or seal of C by 2 elements, then we say that that node is deficient. Then we say that that node is deficient, and somehow we have to remove the deficiency. Okay. Right. I hope you are not confused. So, let us summarize. So how we say that how B plus tree differs from a B tree? In a B plus tree, the actual data is stored only in the leaf node. So leaf node are also called as data nodes. Right? The root node and the intermediate nodes or the internal node, they contain only keys or indexes. They are not actual data. They contain only keys or indexes. They are not actual data. The actual data is stored only in the leaf node. So leaf node is also called as data nodes. Okay. So the data nodes contain only data. They don't have any pointers. But all the data nodes are interconnected. but all these data nodes were interconnected through a pointer, like a singly linked list or like a doubly linked list. It may be either single linked list or doubly linked list. You can go in either way. Right? Okay. Now, what is the property of an internal node and the root node in a B plus tree? The property of an internal node and the root node will be same as that of the property of a B tree. Right? That is any internal node in a any internal node and the root node can have maximum m children and can have maximum m minus 1 keys. Okay, and any internal node other than the root node can have maximum seal of m by 2 children, minimum can have minimum seal of m by 2 children, and can have minimum seal of m by 2 minus 1 children. Okay, root node can have minimum 2 children and minimum 1 keys. Right? Okay, but what is the capacity of a data node? There is no specific, what do you call, there is no specific rule for the capacity of the data node. The capacity of the data node is not defined in the definition. Right? Okay, but the capacity of the data node need not be same as that of the index node. There is no rule that capacity of the data node should be same as that of the index node. Index nodes are nodes which are other than the data node. Right? So if the capacity of the data node is C, that is C is the upper bound, then at any point of time it should have at least seal of C by 2 elements. Then it should have at least seal of C by 2 elements. Okay, fine. I think it's clear. So with this intro, let us try to go through some examples. So this is a B plus tree of order 3. This is a B plus tree of order 3. Okay. So order 3 means, maximum any node can have 3 children, right? And maximum any node can have 2 keys. Okay. And minimum any node can have seal of 3 by 2 children. Okay. Seal of 3 by 2 is uh, 1.5, which is 2 children. Okay. And minimum any node can have seal of 3 by 2 minus 1, that is 2 minus 1, which is 1 key. 1 key. Okay. But this rule is applicable only for what? This rule is applicable only for root node and internal node. Okay. The minimum for the root node is same as that of the B tree. Right? Root node can have minimum 2 children and 1 key. Okay. What about the leaf node? These are the data nodes. Data node can have uh, how many elements the data node should contain. It is nowhere defined in the B plus tree. Okay. So it is not that the data node should contain the same keys as that of the index node. No, it's not like that. Right? So in this particular tree, these are the data nodes. So data node can have even keys more than that of the capacity of the index node. Okay, these, so in this particular tree, if you see, these are the data nodes. And what are the index nodes? Other than the data node, all these things are index node. This is the index node. Node B is the index node. Node C is the index node. Node D is the index node. Node A is also, root node is also an index node. Okay, fine. Okay. Right. Now, what is the capacity of in this particular tree? The capacity of the data node is 3. C is equal to 3. So capacity of data node, let us call it as C. So the capacity of the data node is 3. That is, data node can have at most 3 elements. Right? And what is the, so this is the upper bound. This is the upper bound. What is the lower bound for C? So it should have at least seal of C by 2 keys. What is C by 2? 3 by 2 is 1.5. Seal of 1.5 is 2. So the lower bound is it should have at least 2 keys. Okay, or elements. So these are the elements. Other things are just indexes. Okay, fine. Good. Now let us see what this particular tree says. See, this is very similar to B tree, but there is a small difference, or you call it as B tree or BS tree, but there is a small difference. Okay. Now, what is this? This, so the node A, it contains 2 keys, 20 and 40. But remember, these are not data; these are just indexes. Okay. And what does this mean? Anything you want to find left of anything, if you want to find which is less than 20, then take this direction. Okay. Again, it will lead to node B. Node B contains only one key, which is 10. Again, this is not data, this is an index. Okay. If you want to look for something which is less than 10, take this direction. Okay. Now, now it's an important thing. Please listen carefully. Now, if you want to find something greater than or equal to 10, then go this path. Go this path. See, previously, till now, what we are discussing, for a particular node, anything less than that particular key value, take the left pointer. Anything greater than that particular key, take the right pointer. But now we are for a B plus tree, this logic will not work out. Okay, anything less than the key value, take the left pointer. Anything greater than or equal to the key, take the right pointer. Because this is not only this is only index, this is not data. This is not counted as a data, this is just an index. Are you getting? So now, so it is the right pointer not only refers the element which are larger than the key, but it also refers the element which are greater than or equal to the key. Okay, so this is less than, this is greater than or equal to, right? Okay, fine. Similarly, here if you see, this is less than 20 means go this direction. If you want to find something which is greater than or equal to 20 and less than 40, then take this path. Take this path. Okay. If you want to find something which is less than 30, take this path. If you want to find something which is greater than or equal to 30, then take this path. Right? Okay. If you want to find something which is less than 40, take this path. If you want to find something which is greater than or equal to 40, then take this path. If you want to find something which is less than 70, take this path. If you want to find something which is greater than or equal to 70, then take this path. Okay. If you want to find something which is less than 80, take this path. If you want to find something which is greater than or equal to 80, then take this path. Right? So this also you should remember for B plus tree. Okay. Right? Now let us see how to search some element in a B plus tree. So searching is similar to BST, binary search tree, with the only difference the left subtree contains the element which is less than the key, but the right subtree contains the element which is greater than or equal to the key. Okay, so left subtree, I'll call it as LST. Left subtree contains the element which is less than key, less than the key, whereas the right subtree will contain the element which is greater than or equal to key. Is greater than or equal to key. Okay. So this is the only change which you have to incorporate when compared with that of the BST. Okay. So with that knowledge, let us see how to search some element. Right. Fine. So let us say that we want to search 80 from this B plus tree. Okay. Start with the root node. 80 is greater than 20. 80 is greater than 40. So 80 is greater than or equal to 40. If it is greater than or equal to 40, you have to take this path. So take this path here. 70 is 80 is greater than 70. 80 is equal to 80. But is this is a data node? No, it's not a data node, it's an index. Okay. So you cannot stop here. So again you have to take right. Because the rule says that the data is available only in the data node. Okay. So now which direction you have to take? Should you take to the left of 80 or right of 80? Greater than or equal to means you have to take right. Okay. So 80 is equal to 8, but still you have to take the right direction. Now take the right. Here you see 80 is there or not? Yes, 80 is there. So now you say that yes, 80 is in the B plus tree. We found the element 80. Right? Fine. Okay. Now let us see how to search 10. 10. 10 start with the root node. 10 is less than 20. Take the left path. Now here this B node contains 10. But is this is a data? No, it's not a data, it's an index. So what we are searching is 10. 10 is equal to this. So which direction should we take? Left or right? This left contains only which is less than 10. But right may contain something which is greater than or equal to 10. So we have to take the right path. But if you see the right, there is no 10. There is no 10. So what should we say? This is the data. This is not data. This is just index. So now we should say that 10 is not found. We should say that 10 is not found. There is no 10 in the tree. Okay, this is just a pointer. It is that 10 in the B node is not is just a pointer or the index which says that if you want something less than 10, take the left path. If you want something greater than or equal to 10, take the right path. Okay, it is not necessary that 10 should be there. It may be there or it may not be there. Is it clear? Okay, fine. Right. So we'll take one more example. Let us say we want to search 40. So where is 40? 40, 40 is greater than 20. 40 is here. But is this is a data? No. So then we should take which path? Greater than or equal to. So take right. So now if you will end up with 70, 40 is less than 70. So take the left path. So here is 40. Now you say we found 40. 40 is in the tree. Right? So this is how we perform such operation in a B plus tree. Right? Okay. Let us see how do we perform insertion. Let us see how do we perform insertion. Okay. So so insertion, we perform insertion only in the leaf node because only leaf node is the data node. So just to follow the searching principle just we have discussed, similar to that, and identify the location where the new node should be inserted, where the new element should be inserted. Okay, new element should be inserted in one of the leaf node. Right. Now when you insert the new element into the leaf node, two things may happen. If the leaf node already contains element less than its original capacity, if the leaf node already contain that many elements which is less than its original capacity, then no issue. You can just insert the new element at the appropriate point, at the appropriate location, or after inserting you can sort it. That's it done. Right? Okay. But if the leaf node already contains that many number of elements which is equal to its capacity, okay, that many number of elements it is equal to capacity, then it means that the leaf node is already full. Okay, now you cannot add one more element. If you add one more element, if you add one more element, then there will be overflow. Then there will be overflow. Now how to deal with this overflow? How to deal with this overflow? If such overflow occurs, if such overflow occurs, what should you do? You pretend that the new node is added. You pretend that the new element is added, not node. You pretend that the new element is added. After that, we split the node into two halves. Okay, we split the node into two halves. Okay, so the first half contains, the first half is one node. Now the node is split into two halves, first half and the second half. Okay, the first half of the node, I mean this part of the node, this node, it contains elements with smaller keys. Okay, this contain element with smaller keys, and this node will have element with larger keys. Okay, so let us call this as q. The one with smaller keys let us call with q. Let us call as q. One with larger keys let us call as p. Okay, right. Now from the node which contains the larger keys, which node contains larger keys? The node p contains largest keys. Okay, from that node identify the smallest element. What is the smallest element? Obviously the first element will be the smallest element, right? Take a copy of this element. Take a copy of this element and insert that in the root node. So insert that in its parent. Let us call its parent is R. Insert that element in its parent at the appropriate position. At the appropriate position. So let us call it as Ki at appropriate position Ki. Okay. So this and this both will be same. If this is Ki, this is also Ki. Okay. So Ki's right pointer will point here because now this node contains value which is greater than or equal to Ki, and Ki's left will point to this node. Ki's right will point to P, and Ki's left will point to Q. Okay, this is what we are going to do. Right? Fine. So that is what being explained here. If overflow occurs, then split the node into two. Okay, that is P and Q. P contains the element with largest keys, and Q contains the element with smallest key. Okay, and from P is the node which contains the element with largest key. From Q, identify the smallest element and move that to the parent. Okay, the smallest element of P, you identify that and move it to the parent and add a pointer in the parent, such a way that that key is, I mean, whatever greater than or equal to that key will point to the node P, right? So let us see this with an example. Let us see this with an example. Say, say a leaf node contains, sorry, say a leaf node contains these values 10, 13, 15, and 17. And assume that C is equal to 4. That is, the capacity of the leaf node is only 4. Leaf nodes are the data nodes. That is, it cannot take more than that. Now, if you try to insert 20, then there will be overflow. Right? Now we split the node into two. What are they? We will split something like this. 10 and 13 will be 1. Okay, so this is Q as per our nomenclature here. This is Q, this is P. Okay, so so 10 and 13 will be Q, that is one with the smaller keys. Okay, 15, 17, and 20. 20 is the one that you want to insert. That will be the another node. Okay, so that we will call it as P. Okay, now from P, identify the smallest element, which is 15. Okay, that 15 should be moved to the parent. So parent already may have many keys, but apart from that, 15 will also be added to the parent, right? Now 15's left will point to Q. Okay, because this contains less than 15. 15's right will point to P. That is, it contains element which is greater than or equal to P. Okay, so this is the whole logic behind insertion. Let us discuss this with an example. So it is quite similar to B tree. Only thing is, what in B tree we'll be removing an element and we'll be keeping in the top. Okay, but here we are not removing. We are keeping a copy of that. Okay, we are keeping a copy of that after I mean after splitting. After splitting, keeping a we are keeping a copy of that, and then we are making the right pointer to point to the right right child. Okay, now the right child is not only contains the element which is greater than the key, but it contains element which is greater than or equal to the key. Okay, right. So let us see how to insert 27 into the below B plus tree. Okay, so 27 is greater than 20, is less than 40. So take this path. 27 is less than 30. So take this path. Okay. So let us assume the capacity of the node is 3. Okay. Let us assume the capacity of the node is 3. That is the node can have 3 children. Okay. And also let us assume the order is 3. Same, whatever we have discussed in that. Okay. The order of the B tree is 3. That is, other node can have maximum 2 keys, not more than that. Okay. I mean, all the index node uh, can have maximum 2 keys and minimum 1 keys, right? Okay. So 27 should be inserted here. Okay. See this node, its capacity is 3 and it contains only two, two, two elements. Its capacity is 3 and it contains only 2 elements. So is there a space to insert? Yes, there is a space to insert. So 27 can be just inserted here, nothing else. So this is a very simple case. So this is how we insert something into the B plus tree when the leaf node is not full. So here after insertion, there is no overflow condition occurred. Okay, so the insertion is done. Right? Fine. Now let us see, we want to insert 14 to this particular tree. So where to insert 14? Start with the root. 14 is less than 20, so take this path. 14 is greater than 10. Greater than 10, so take this path. You have to take this path. But if you see this node, it is already full. The capacity is 3. It is already having 3 elements, 12, 16, and 18. Okay, so now we cannot insert. So what we should do? But we pretend to be inserted. So 12, and then what is the new element is 14. 14. See, this can be represented either vertically or horizontally. There is no issue in that, right? Here it is given vertically, you can also put it in horizontal. Okay, 12, 14, 16, 18. Okay, 12, 14, 16, 18. Right? Okay. So this is the new node which you get, but it is the overflow. It is the overflow condition because the capacity is only 3. Now what we should do? split this into 2. So if you split this into 2, 12 and 14 will become one node, and 16 and 18 will become another node. Okay. And also what should happen? So as per our previous discussion, this is Q, this is P. Okay. The smallest element of P should go to the parent. What is the smallest element of P? 16. 16 will go here. 16 will go here. Okay. And to the right of 16, what we'll have? This port, P port will have. That is 16 and 18 will have. 16 and 18 will have. To the left of 16, what we'll have? We'll have only 12 and 14. We'll have only 12 and 14. Okay. So the left of 16 will have 12 and 14. The right of 16 will have 16 and 18. Right. So this is how we insert 14. Right. So you can see the tree. After inserting 14, what you get? 16 moved to the parent. A copy of 16 is moved to the parent. To the left of 16, we have 12 and 14. And to the right of 16, we have 16 and 18. Okay. You can observe this, all these root nodes are, all these data nodes or leaf nodes are connected through a double, doubly linked list kind of counting. Right? Okay. So this is the case after inserting 14. Right? Now let us see in this particular tree how to insert 86. 86. So 86 is the one which you want to insert. So 86 is greater than 20. It's, it's greater than 40. So we have to take this fourth. 86 is greater than 70. 86 is greater than 80. So we have to take this fourth. But if you, so we have to keep 86 here. Okay. But if you see this particular node, is it already full or not? Yes, it's already full. So this particular node is already full. Here it is full. So you cannot insert. But as usual, we'll pretend to insert. So 80, 82, 84, 86. 86 is the new one. That is 86. I'll mention in different color. Okay. But it is a overflow condition. It is an overflow condition. So whenever there is an overflow, what should we do? We should split the node into two. We should split the node into two. So we'll split the node into two. So one part which contains the node with lesser key values, and the other part and the other node which contains the node with the larger key values. So this is P and this is Q. Okay, this is P and this is Q. Okay, right. Now, after splitting, 80's right will point to what? 80 and 82. 84 is not there. Okay, this smaller element of Q. Sorry, I'm sorry, I'm using wrongly. Let us go with our nomenclature. This is the left is Q, the right is P, right? Okay, this is Q and this is P. Okay, the smaller element of the larger key values, that is this 84, should go to the parent. Okay, so 84 will come here. 84 will come here, and the right pointer of 84 will point to 84 and 86. It will point to 84 and 86. That is fine. Now the deficiency is removed here at this level. But what about this node? Is it deficient or not? This is a B tree of order 3. B tree of order 3. It's a B plus tree of order 3. It means all the index node can have maximum how many keys? They can have only two keys. They cannot have more than two keys. Okay. So here what happens? There is a so this node has become now deficient. Okay. So now how will we remove the deficiency? Again, this node should be splitted. Okay. So how you will split this node? Okay. How you will split this node? So we have to split as 70 and 80 and 84. 70 will be one half, 80 and 84 will be another half. Okay. So this node should be splitted now. So how we are going to split this? How we are going to split this? 70 will be one node, new node. 80 and 84 will be another node. 80 and 84 will be another node. Okay, right? Okay, so less than 70 will point here, right? Less than 70 will point here, and mm, greater than 70 will point to this. Okay, and also this 80 will go away. 80 should go to the top also. Okay, 80 should go to the top also. Okay, right? So if 80 goes to the top, again if 80 goes to the parent, 80 will come here. 80 will come here. Okay, 80 will come here, right? So so left of 80 will point this, and right of 80 will point this, right? Okay, right? Okay. So so here to the right of 80 we have this. To the right of 80 we have this 80 and 82. Okay. To the right of 84 we have 84 and 86. To the right of 84 we have 84 and 86. What is there to the left of 80? What is there to the left of 80? Okay, fine. See here what happens in the sense. See, see everything is fine. To the here to the right of 84 we have 84, 86. Okay, right. When 84 is added here, this node has become overflow. This node has become overflow. So we are splitting into two. 70 is one. This we call it as Q, and this we call it as P. Right. Now this 80 will be moved to the top. Right. See, this 80 is the index. This is not a data. Okay. So index we maintain only one copy. Index we maintain only one copy. Will not have more than one copy of index. Okay. So and that one copy will be maintained in the in the whatever the available topmost level. Okay. So now 80 is repeating at two places. 80 is repeating here and here. So one of the 80 should be removed. One of the 80, this is just an index. It is, we are not deleting anything. We are not just representing it. Okay. So which 80 should be removed? The one in the child should be removed. So this 80 will be removed. Removed. Okay. Because after splitting this into two halves, the smallest element should go to the parent. Okay. Now these two are both are indexes. It is not in the previous case that is not the case. Here 84 is an index. This 84 is a data. So we are keeping in both places. But here this is an index. This is also an index. So index we maintain at only one place, and that will be in the available upper level, in the higher level. Okay. So this 80 we are removing, right? Okay. So now 70's left is this, 70's right is this. There is no 80 here. 84's left is this, 84's right is this, right? Okay, fine. But now if you see what happened to the root node, there is a overflow in the root node. There is a overflow in the root node. Now root node should be split into two. Now root node should be split into two. Okay. So how will you split? Again, this will become what? 20 and 40 and 80. Okay. This is Q and this is P. Right. So the smallest element of P should go to the top. So that is what? 40. So 40 will go to the top. To the left of 40 we'll have 20. To the right of 40 we'll have this. Again, if you see this 40 is repeating. Again, this 40 is what? Index. So we'll remove this. We'll remove this. Okay. So to the left of 40 we'll have 20. To the right of 40 we'll have 80. Okay. To the left of 20 we'll have B. To the right of 20 we'll have C. This part is same. Okay. Right. To the left of 80 we'll have 70. Right. And to the right of 80 we'll have 84. Okay. So this is the updated tree after inserting 86. You can see the level has increased by 1. To the root is 40. To the left of 40 we have 20. To the right of 40 we have 80. Okay. To the left of 20 that 40 same 10, 16. To the right of 20 we have 30. Okay. To the left of sorry, I'm going to the wrong place. Okay. To the right of uh, to the right of 40 we have 80. Okay. To the left of 80 we have 70, and to the right of 80 we have 84. Okay. So to the left of 84 we have 80 and 82, right? To the right of 84 we have 84 and 86. So this is the updated tree after inserting 86, right? Okay. So that's it about insertion. We have discussed all cases, right? Now let us see about deletion. Okay. So in deletion, when you remove some keys, it may become in insertion overflow occurs. Okay, when you insert, overflow may happen. Okay, but in deletion, when you remove some of the element, some of the node may become deficient. Okay, right? So a non-root index node. A non-root index node means which is not a root node, but it is any intermediate node. When it will be deficient, it is same as that of the rule of the B tree. It will be deficient. Uh, it will be deficient. A non-root index node is deficient when it has less than seal of m by 2 minus 1 keys. Okay, it's less than. It's less than. Okay, it can have up to seal of m by 2 minus 1 keys, right? So a non-root index node will be deficient when it has less than seal of m by 2 minus 1 keys. Okay, and a root node is deficient when it has 0 keys. Root node is deficient when it has 0 keys. Data node is deficient uh, when it has less than, again this is less than seal of c by 2 keys. Okay, so this is the situation under which the I mean deficiency occurs in a when in case of deletion. Okay, so let me update this. Sorry. So a non-root index node is deficient when it has less than seal of m by 2 minus 1 case. It can have up to seal of m by 2 minus 1 case, right? Which is same as that of B3. Root node is deficient when it has 0 keys. Data nodes are deficient when it has less than seal of C by 2 keys. Okay, when it has less than seal of C by 2 keys. Okay, where C is the capacity of the node. Where C is the capacity of the node. Okay, fine. So yeah. So by the way, this also will update. So this should be Q and this should be P. Okay. Okay. Sorry for disturbance in between. Okay. So this is the rule for deletion. Okay. When you delete a node become deficient, deficiency in index node occurs when it has less than seal of m by 2 minus 1 keys. Deficiency in root node occurs when it has 0 keys. Deficiency in a data node occurs when it has less than seal of c by 2 keys, where c is the capacity of the data node. Say from this particular tree, we want to delete 40. We want to delete 40. Where is first locate 40? Where is 40? 40 is greater than 20. 40 is here, but this is not data, this is a index. Okay, so we have to follow the right tree because right tree may contain the value which is greater than or equal to that. So take this path. Okay, so if you take this path, we reach 70. 40 is less than 70. Okay, so search here, 40 is here. 40 is here. Okay, so what is the capacity here? What is the capacity here? Capacity of the data node is 3. Okay, that is maximum it can have 3. Minimum it can have how many? Minimum it can have seal of 3 by 2. That is it can have 2. It can have 2 elements. Okay, so if you remove 40, this particular node will have 2 elements. So there is no issue in deleting 40. You can just delete it because after deleting also it has sufficient elements. There is no deficiency. After deleting also no deficiency is created. Okay, fine. Say from this below tree we want to delete 71. Locate 71. 71 is greater than 20. It's greater than or equal to 40. So I mean it's greater than 40. So follow the right direction. It is here 70. But again this is what? Again this is 71. We want to delete 71, not 70. Okay. So 70 is we take this path. It's greater than 40. So when we reach 70 here, 70 is greater. 71 is greater than 70 and is less than 80. So it should be in this node. Okay. Yes, it is here. Yes, it is here. But if you delete it, what will happen? When you delete this node becomes deficient. Okay, because the capacity of the data node is 3. So minimum the data node should contain how many? Minimum the data node I'll mention as D. It should have seal of 3 by 2. That is minimum it should have 2 elements. After deleting it has only one element. Okay. So now this deficiency should be removed. How can we remove the deficiency? Can it borrow from its either left sibling or right sibling? Yes, it can borrow both from left sibling and also right sibling. Okay, because if any one of them want to donate, they should have they should have at least uh, they should have at least a seal of m by. They should have how many keys? They should have at least after donating after donating also they should have seal of m by 2 keys. Okay, then they can donate. Okay, they should have at least seal of m by 2 plus 1 keys, which is nothing but C. Okay, so here we can borrow. Okay, so let us assume that we are borrowing from let us assume that we are borrowing from the right sibling. Let us assume, so we can borrow either only from the left sibling or from the right sibling. So let us assume we are borrowing from the right sibling. So when you borrow from right sibling, we perform left rotation. So when you perform left rotation, this 80 will come here. This 80 will come here. Okay, so if 80 is moved here, if 80 is moved here, okay, now this 80 is just a key. No more this 80 is available. No more this 80 is available here. Okay, right? Or you can say that, or instead of saying like that, we can say that this 80, this is index. This is not a what do you call this is index, and this is not a value. Okay, this is not an element. Okay, but still, as per the property of left rotation, we say that this 80 is moved here. So 71 is deleted, 80 is moved. Okay, so it means that this 80, this element has moved here. Okay, it means this element has moved here. Okay, so no more, so no more. Here we have this 80. 80 we don't have, right? Okay, so this 80 should be replaced with what? This 80 should be replaced with 82. Okay, because it should contain what? It should contain something which is greater than or equal to that. Okay, you cannot keep 80 here because here we have 80, right? So it should have 82, right? So after deleting 71, now the tree is balanced. Now there is no deficiency. Okay, so this is how we delete 71. So you can see here after deleting 71, 82 comes at the index level, and to the left of 82 we have 70. We have 72 and 80. This should be sorted. Okay, this should be sorted. So actually 80 will come here. We have 72 and 80, and to the right of 82 we have 82 and 84. Right? Okay, fine. Next, let us see how to delete 80 from this particular tree. Okay, so where is 80? Okay, so this is after deleting 71. Okay, so uh, so let us see how to delete uh, 80. 80 deleted. Okay, fine. So let us take this tree. Okay, so here in this tree itself we are going to delete 80. In this tree itself we are going to delete 80. Okay, so how we are going to delete 80? So this is the case after deleting 71. Okay, this is the state of the tree after deleting 71. But now we want to delete 80, right? So if you want to delete 80, first identify where is 80. 80 is greater than 20, it's greater than 40, so take this path. It's greater than 70 and less than 82, so take this path. Now if you remove 80, now if you remove 80, this node will become deficient. Okay. Now can it borrow from its right sibling? No, it cannot borrow. Can it borrow from its left sibling? Yes, it can borrow from its left sibling. Okay. If it borrows from the left sibling, then we perform what? Right rotation. We perform right rotation. Okay, then this 70 will come down. So this will become 70 and 72 will be here. 72 will be here. Okay. So, but there is no such 70. If there is any 70 node, there is no 70. Okay. So, so, so actually this is not possible. Okay. Because there is no 70 value. If there is 70 value here, there is no value like 70. Okay. So, so, so moving of 70 is not possible. Okay. So actually then what should we move? We should move 40. What should we move? We can move 40. So if you move 40, then what will happen? Then what will happen? As there is no 70, so we have to perform right rotation, right? So this 40 will come here, okay? But this is index, and the actual 40 will come here, and the actual 40 will come here, 72 will come here. Okay, and the 40 will be removed from here, and the 40 will be, oh, I'm sorry. See, if this is what 70. So here you have to find, you have to what? If you are, if you are borrowing from the left sibling, if you are borrowing from the left sibling, you have to take which value? The highest value. You have to take the highest value, not the lowest value. Okay. So let us put it in the horizontal way. If you put it in the horizontal way, it will be what? 40, 50, and 60. It will be 40, 50, and 60. So the highest value will come. Okay. So it is nothing but a in order predecessor. Okay. If you are borrowing from the right, then it is in order successor. Okay. It is, so we have to take the highest value from the left child. Okay. If you are borrowing from the right, then you can take the lowest value from the right subtree. Okay. So we have to take 60, not 40, right? So 60 will come here as an index, and 60 also will come here. Okay, 80 is the one you are deleting. 60 also will come here, and 72 will come here, right? Right, 60 will be removed from here. So this is how it works if you borrow from the left sibling, right? Okay. But actually, in the textbook, they are not following borrowing from the left sibling. Okay, they are not following that approach. Instead, we are going to merge these two. Okay? Because we want to learn how the other things happen, right? You can borrow from the left sibling, that is fine, like how whatever we have discussed. The 60 will come here, and also it will come here. 60, 72 here we will have. That is also correct. Okay, but let us see that. Let us the in the textbook approach, as this 80, after deleting 80, it cannot borrow from the right child. So we are going to now merge these two. Okay, we are going to merge these two. Okay, if you merge these two, what will happen? 72, 82, and 84 will be there. Okay, normally when we merge, we will bring the parent also down. Here the parent is nothing but same 82, so there is no point in bringing it down, right? Okay, it is just an index. It's not anything new. Okay, so to the right now, to the right of 70, we'll have what? 72, 82, and 84. Okay, to the right of 70, we'll have 72, 82, and 84. Okay, so so that will be the right of 70. To the left of 70, it will be as usual same. Okay, so and this what do you call, this 82 will be removed. This 82 will be removed. Okay, I think there is no deficiency. So this is the resultant tree after deleting 80. Okay, you can delete 80 this way also, right? So instead of borrowing from the left sibling, we are merging the this particular node and the right sibling. So this is the resultant tree. To the left of 70, we have 40, 50, and 60. To the right of 70, we have 72, 82, and 84. Okay. Next, let us see how to delete 32 from this below tree. Right. Okay. Uh, so, so this is the tree which we got after inserting 86. If you recall, after inserting 86, this is the tree which we got. Okay. In this tree, from this tree, we want to delete 32. Okay. So how we are going to delete 32? Right? 32 is less than 40. Take this path. 32 is greater than 20. Take this path. 32 is greater than 30. So take this path. It should be here. Yes, it is here. Now, if you delete 32, this node become deficient. Can it borrow from its? It does not have a right sibling. Can it borrow from its left sibling? No. Left sibling has exactly a seal of C by two keys. If it donate one keys, it will become deficient. So it cannot borrow. So what should we do? We should merge. Okay, we should merge. So if you merge, what will happen? This will become what? 20, 25, and 36. Okay. If you merge, it will become 20, 25, and 36. Okay. So after merging, what you will have is 20, 25, and 36. This is what you will have. Okay. Right. Now, what will be in the top? What will be the parent? What will be the parent? Okay. When you what will be the parent? So the parent is see here. If this parent is just a index, it is not a data. Okay, it is not a data. So we cannot we are not going to bring this down when you are going to merge. Okay, we are not going to bring this down, so it is merged. Okay, 20, 25, and 36. Okay, you can keep it to the left of C. You can keep this 20, 25, 26 to the left of C, but there is no such 30 here. There is no such 30. There is no value here. Okay, because there is only one pointer. When you can have one pointer if there are zero keys. Are you getting? Right? If there are m minus 1 keys, then you can have m children. So you have only one children, then how many keys is supposed to be there? Zero keys. Okay. So with that logic also you can see. Okay. And why we are not bringing 30 down? Because there is no data as 30. Right. So there is no key here. Okay. So if there is no key here, then that is a deficient. That is a deficiency, right? There is minimum it should have. This is a index node. So minimum it should have seal of m by 2 minus 1 keys. Okay. It's a B tree of order 3. It's a B tree of order 3. So minimum it should have one key, but it does not have. Okay. Now, can it borrow from its left sibling? It has only left sibling. It does not have a right sibling. Can it borrow from its left sibling? Yes, yes, it can borrow from its left sibling. Okay. So, if it borrows from its left sibling, what will happen? It can borrow from its left sibling, right? So if it borrows from its left sibling, then how the tree will be converted? Okay, so that's what we are going to discuss. So if it borrows from its left sibling, what will happen? This 20 will come down. Okay, this 20 will come here. It's the index only, but still it comes here, right? Okay, this 16 will go here. Remember, 16 is a data. 16 is a data. Okay, 16 is a data. Okay, so this 16 will be removed because index we already discussed, it should be only at one place and it will be always available in the highest level. So whenever an index is moved to the highest level, the index from the lower level will be removed. The index in the lower level will be removed. Okay, now if you are removing this index, where this left subtree will go? I mean, where this right subtree of 16 will go? Okay, the right subtree of 16 will now become the left subtree of 20. Okay, the right subtree of 16, now it will become the left subtree of 20. Okay, and this this new node 20, 25, 36, it will become the right subtree of 20. Is it clear? So this is what it's going to happen. Okay, so all these changes happening because of removing 32. So when you delete 32, this node is becoming deficient. So you are merging this. Okay, so when you merge, this node is gone. Okay, so 20, 25, 36 here we have, but there is no index here. Okay, because it has only one child. Only when there is zero index, you can have one child. Okay, so as there is no index, there is a deficiency. Now, can it borrow from its left child? Yes, it can borrow. So this 20 is coming down. 20 is an index, it is coming down. Okay, and this 20 is replaced by 16. Now 16 is a index and also a data. So index can be at only one place. So and it should be at the higher level. So we will leave this 16 and we will delete this 16. Okay. Now where this right child of 16 will go, that will become the left child of 20. Okay. And this part will become the right child of 20. Right. So that is the resultant one. Okay. So this is the intermediate case after merging. Right. And after rotating or after borrowing, this is what we got. Okay, so what we have is 16 to the left of 6 uh, I mean to the left of 20 we have 16 and 18, to the right of 20 we have 20 and 20, 25 and 26. Okay, right. So this is after deleting 32. Okay, next let us see how to delete 86 from this below tree. Okay, where is 86? 86 is greater than 40. Take this path. 86 is greater than 80. So take this path. Okay, 86 is greater than 84. So take this path. 86 is here. Now, if you delete 86, what will happen? This node becomes deficient. Okay, can it borrow from its left sibling? It has only left sibling. No, it cannot borrow because already it has exactly seal of C by 2 keys. Okay, so you have to merge. So if you merge this, there is no this node, 84 will come here, right? And now this node has only one children, so there is no key here. There is no key here. 84 is removed. Okay. Now this node has become deficient. Node E has become deficient. Now how can we remove the deficiency? Can it borrow from its left child? No, it cannot borrow. So what should we do? We have to merge. We have to merge. Okay. If you merge, what will happen? If you merge, what will happen? 70 and 80 will be combined. Okay. 70 and 80 will be combined, right? I mean, this 80 is going to come down, right? Because 80 is also a data. 80 is also a data. Okay. 70 and 80 will be merged here. Okay. 70 is left is this, 70 is right is this, 80 is right is this. Okay. This is not, all this not there. This 80 will be removed. Okay. This 80 is removed because we are merging. We are merging. Okay. We are merging. So this 80 is removed, right? Now this node has become deficient. Now this node has become deficient. So how will you remove the deficiency? Can it borrow from its left sibling? No, it cannot borrow. So once again, we should merge. So if you merge, what will happen? 40 will come down. Okay, 40 will come down, and this will become empty. Okay, so as per the rule, empty root node can be removed. As per the rule, empty root node can be removed. Okay, so we will just remove that. We'll just remove that. Okay, and to the right of 40, what we'll have? This 70 and 80. Okay, that's all. So this is the result you will get. Okay, and that now the root node is 20 and 40. All these are not there. Okay, now the root node is 20 and 40. Left of uh, left of 20 is same, right of 20 is same. Okay, right of 40, what we have? 70 and 80. To the left of 70 we have 40, 50, 60. To the right of 70 we have 71 and 72. To the right of 80 we have 80, 82 and 82. Okay, so this is how we perform deletion, okay, from an B plus tree, right? So that's it about B plus tree. Okay, I think let us stop here. Thank you.